Welcome to session 11 of data communication. Today we'll be looking at routing in switched networks. Now, routing is a complex, crucial aspect of packet switched network. Routing deals with how packet moves from one station through the switching network to the other station, going through various hubs or various stations or networks before getting to its destination. So we are going to see how important routing is in data communication. Some characteristics that are required are the correctness, the simplicity, its robustness, its stability, some fairness, then optimality with some efficiency. Now, there are two performance criteria that are used in selecting which route a particular packet is supposed to take to get to its destination. The first performance criteria is the minimum hop count, or the minimum hop, and this one passes, or the minimum hop is one that passes through the least number of nodes through the network, and we'll explain how that is going to be like. Minimum hop also minimizes the consumption of network resources in terms of bandwidth. Then we are going to look at the least cost, which is the second performance criteria. Now, the higher the data rate on your link, the lower the assigned cost of the link. So we are going to actually see a setup of networks with various costs attached to them. And we are going to find out how these two performance criteria are going to help us get the path, or the path a packet will pass at the least cost. This is an example of a packet switch network. Here we have node 1 through to node 6. And so these are the various nodes. You can call them vertices in terms of graph. And these are the link. These arrows shows the link. Now, in terms of graph, we deal with, at each node, we talk about the in degrees and the out degrees. The in degrees is when an edge comes into a node. An out degree is when an edge is leaving the node. So, taking node 2, for example, node 2 has an in degree coming from here and has an out degree going this way. On the other hand, it also has some out degrees with respect to node 2. We have an out degree also coming this way. So it has both an in degree and an out degree to N1, and it has an in degree and an out degree to N3. The numbers you are seeing there are the cost associated with the link. So we are going to find out how to calculate the shortest path from node 1 to node 6 and at the least cost. If you realize node 1 to node 6, we can have so many options of going to node 6. So we can go through N1, N2, N4, N5 to N6. We can also do from N1 straight to N3, then to N6. But are these the shortest path? And are these going to give us the least cost? We are going to look at how to do that. Now, we want to look at decision time and place. Now, there are two key characteristics of the decision on routing. And these are the time and the place that the decision is made. Time has to do with whether it's a packet or virtual circuit based timing that we are using, whether it's packet switch or virtual circuit. If it's packet switch, we know whether it's datagram or virtual circuit also. Now, the place, we are talking about whether it's distributed, whether it's centralized, or whether it's from the source. Now, in a distributed routing, each node has the responsibility of selecting an output link for routing packets as they arrive. It's able to distribute nodes, and each node that has the responsibility of selecting an output link for routing the packets as they arrive. For centralized routing, the decision is made by some designated node. And this can be a network control center. So it's like having a pool of routes, and you make a request to that pool. So for instance, if I'm going to say Accra, I go to say Medina Station. There are a whole lot of destination or cars there. I can pick one of them. Depending on which route the driver uses, I get to Accra. So it's like they are having pools of destination in there, and I'm able to, per my request, they're able to direct me as to where to go. Then we have the source routing, and here decision is actually made by the source station rather than by a network node, as we saw in the centralized routing, and is then communicated to the network. Now we want to look at some network information source and update timing. Now routing decisions usually are based on the router having knowledge of the network, also having knowledge of the traffic load and the link cost, or what we are calling the least cost or the edge cost. Now, for distributed routing, the nodes use the local knowledge, which is the cost of the outgoing link, and may collect information from adjacent nodes, probably information on congestion, and may collect also info from all nodes on a potential route or route. Now for central routing, it collects information from all nodes. Mind you, it has to house the destination. So it has to get information from the various nodes and store it in its CAM table or its routing table. Then for update timing, when a network info is held by nodes, for central routing, we collect information from all nodes. Mind you, it has a centralized table where it stores all the destinations and source IPs. So it kind of like have a routing table where it feeds in majority of the routes into its table. So it always needs information from all nodes that are connected to it. Now when do we update the tables? Now when is a network info held by nodes updated? We have the fixed strategy. The info source is never updated. Then we have the adaptive strategy. Here we have regular updates of info. So if today I use probably I'm going to circle and I pass through 37 and there was congestion there, or they are doing road work there. Next time I need to update the routing table and tell it that, okay, it will cost me, or I'll waste time using 37. So let me go through probably another route. And this, I update the routing table based on my current situation. And that is the adaptive strategy. Has regular updates of information source. Now let's look at routing strategies. There are 4 key routing strategies that has evolved for dealing with the routing requirements of packet switching networks. We have the fixed strategy, we have the flooding, we have the random, and we have the adaptive. Now for fixed routing, we have a single permanent route for each source to destination pair. And this determines the route using the least cost algorithm. We'll be looking at how to use that. It has a route fixed at least until a change in the network topology is employed. So with fixed routing, we have a single permanent route. It makes use of the least cost algorithm. Then, anytime it has to change its network, or anytime it has to change its routing table, it means that the entire network topology is being changed. Now, there's no difference between the routing for datagrams and virtual circuits. Its advantage is its simplicity, and it should work well in a reliable network with a stable load, just a small network with small nodes. Its advantage is that it lacks flexibility. It does not react to network congestion or failures. We'll look at one of the routing strategy that solves this problem. Let's look at flooding. With flooding, I get to do what is called broadcasting. Each router, when it gets the packet, it sends it to all its outgoing link. Now, the incoming packets are retransmitted on every link except the incoming link. Now here, eventually, a number of copies will arrive at the destination. So we are looking at duplicates. Because once I send it to you, when you get the packet, you also broadcast it on your link. When the other person gets the packet, he also does the broadcasting until it gets to its destination. And if there are different routes to that destination, eventually that destination will have multiple copies of the frame or the data being sent. Now each packet is uniquely identified or is being numbered so that these duplicates can be discarded. So if I am 1 and I send to 2, because the packet is coming from 1, I will add my tag to it. Now 2 will also take the packet and add his tag to it. So it becomes something like 1.2, meaning that, oh, it came from 1 and 2 is now broadcasting. So once it gets to the destination, if there are duplicates, of course, it uses the uniquely numbered tag on them to show that, okay, this is the latest one, or this is a duplicate, or this is not a duplicate. And this can include a hop count in packets. Nodes can remember packets already forwarded to it to keep network load in bound. This is an example of the flooding. So you realize that we have this node. It received the packet, but it has broadcast the packet to every other node. So you realize that we have 3 coming here, we have 2 coming here, we have 1 coming here. When it gets here, there's another broadcast. So at the end of the day, we have so many packets joined up here. Of course, this will be numbered. So once it gets to 6, 6 knows that, okay, probably this packet is the same as this packet, or this packet is the same as this packet, and that it discards them appropriately. What are the properties of flooding? Now, all possible routes are tried and are very robust. At least one packet will have taken minimum hop count and hence can be used to set up virtual circuits. Now, all nodes are visited and therefore useful to distribute information, which is the routing. Then let's look at the random routing. Here, the nodes select one outgoing path for retransmission of the incoming packets. Here, the nodes are not broadcasted, but we select one path to be able to send the packet onto that link. Now, selection is based on a round-robin approach or a random approach, and this can select outgoing path based on a probability calculation. Here also, no network information is needed, and route is typically not least cost nor minimum hop. Then we look at the adaptive routing, and this is used by almost all packet switching networks, and routing decisions change based on some condition of the network. First is the failure, and second is the congestion. So when there's failure on a network or on a link, the routing decision changes. Also, when there's congestion, the routing decision changes. Now, with adaptive routing, it requires information about the network. What are the drawbacks? Decisions here are more complex and it increases processing burden. The trade-off between the quality of the network information and the overhead causes performance degradation. Reacting too quickly can also cause oscillation, and it's too slow to be relevant. Its advantage is that it has improved performance, it aids congestion, and has a complex system. You may not realize theoretical benefits from them. Now let's look at least cost algorithm. And this is the basis for routing decision. We've already seen the two performance criteria, the minimum hop and the least cost. And this can minimize hop with each link cost of say 1, and can have link value inversely proportional to the capacity or the bandwidth. Now, given network of nodes connected by a bidirectional link, where each link has a cost in each direction, we are going to look at an example of how we are going to calculate the least cost. Now, we define cost of the path between the two nodes as the sum of cost of the links traversed. Hence, for each pair of nodes, we find a path with the least cost. Now, the link cost in different directions may be different, talking about the length of the packets.